So today's final talk is given by Professor Bedford from USA. His title is Dynamics of Bifurcation Map of Surface.
Well, thank you very much. I want to thank the organizers for inviting me and making it possible for me to participate in this very enjoyable event. And so I'm very glad to be here. What I would like to talk about is two things. One, well, it's the material I'd like to talk about is joint work with Jeff Diller. And I want to talk about discussing the dynamics of a very specific family of birational mappings. And also I want to just tell you what the general theory of birational mappings of surfaces. So I want to talk about birational mappings of surfaces, and it's a much simpler case than the higher dimensional case. So the specific family I'd like to talk about is this one. This family of mappings. And in fact, what I want to be looking at is looking at this map as a mapping from R2 to itself. Okay, but you know, this is a meeting on complex methods, so I will give you complex methods, but I can't necessarily promise you complex results, but I can give you maybe real results. Okay, so anyway, we'll see. You may take back your 15 minutes yet. So this mapping is reversible. And in this particular, what that means is that the inverse is conjugate to f via an involution, and this particular involution is very simple. Okay, so if you take your mapping and you compose with a flip of R2, this is just a simple flip, you conjugate to the inverse. So that means then that's very nice. That means if you prove something about f, then you just flip the picture and you have the same thing for f inverse. Very convenient. Now, let me describe here the behavior of this mapping. Okay, in other words, okay, so there is f, and here are two copies of R2. And I want to look at R2. I'm going to consider the compactification of R2 as a circle cross a circle. So in other words, infinity and infinity, plus infinity and minus infinity are the same. Okay, so we're making this a torus. Okay, so let me get some of this nice colored chalk. If we look at the line here where x is 1, okay, so when x is 1, the first coordinate becomes infinity, the second coordinate becomes a. Okay, so over here we go to a. So these are the same point, okay? And so this vertical line is taken to this point, okay? And on here, if we look at the point 1, 0, that's this orange thing, the point 1, 0, in fact, is blown up to the whole horizontal line. So this is y equals a. Okay? So this is typical behavior for a birational map. You have a line taken to a point and a point taken to a line. Okay? So that's that one. And we also have if x is minus a, okay, and I'm going to be thinking about a as negative, so minus a will be positive. But say x is minus a, then this goes to 0. So over here we're looking at x equals minus a, and that comes over here. Let me see, just look at my picture here. Minus a comes over here to 0. Okay? This will be the point 0 minus 1. Okay? So that blue line goes to that point. And let me just get one more color. Then these 2 points here at infinity, which is the same point, that point goes to this horizontal line, y equals minus 1. Okay? So we have 2 points that are blown up and 2 lines that are blown down. So I'm just wanting to make the picture, I mean, I'm going to be very concrete today. So anyway, this is the picture of what this map is doing. And as you know, a birational map is looking like you have a space, you remove some variety, and that goes to the space minus some other variety, and then this is a biholomorphism. Okay, so this is what a birational mapping is doing. It's acting like a biholomorphism, except there just happen to be a couple of places where there's a problem. Okay. Now, this particular family of let me see, what am I going to say here? Let me try. Oh yeah. What are the questions here? Okay, questions to focus on about this family of mappings. First off, what is the rate of degree growth? Okay. In other words, we're looking at the degree of the nth iterate of this thing. So we take the n-fold composition of this mapping with itself. And is this equivalent to some, sorry about that. Does this grow exponentially, for instance? Okay, this is a question. And another question you can ask is, what is the nature of the pointwise dynamics? Okay, and that's what I want to focus on later. And the third question you can ask is, a third question actually is very natural. So when you're trying to think of how to approach a mapping like this, because of your education or whatever, you may think that you want to look upon this as being a diffeomorphism and see how far you can go studying this as a diffeomorphism. In that case, you'd study pointwise dynamics. But in fact, if you're thinking of this as a rational mapping, if you're thinking of points as being blown up, it's very natural to consider how does this act on a space of one-dimensional objects. So what is the what is the dynamics on the one-dimensional objects? So this family of mappings was studied in a number of papers by Abarankova. Bukra, Hassani, well, there was a group of mathematical physicists that wrote a lot of papers, or long papers about these mappings. They were very much looking at it with computer methods, and I guess my opinion in looking at that was that here, if I look at this picture, I have a pair of points of indeterminacy. This one point of indeterminacy, if you look at it in backward time, here's infinity, infinity. In backward time, it sort of goes like this. I'm just sort of coming back in time. So in forward time, this point blows up, but in backward time, this point goes off to infinity. This is just a wandering point. Okay? So this one is wandering. And it turns out that this point at infinity is non-wandering, meaning it's recurrent. The point, this is a point of indeterminacy, so something blows up there. But in fact, if you look at it in backward time, this point keeps coming very close to itself. So this is a point that actually contributes seriously to the dynamics. Anyway, so these people didn't have any particular, they were not interested in looking at points of indeterminacy. So it seemed to me that this was a good thing to look at. So. So anyway, that's the plan. Let me see here. Okay. Now, what's the general theory? Well, there was work by Diller and Favre, and they considered a Kähler surface, compact Kähler surface, and a bimeromorphic mapping. Okay. And so I can sort of summarize sort of the brief version of what is known about this situation. They want to look at what's happening on one-dimensional objects, so they're looking at what's happening on positive closed currents. So one thing is that there is, let me see what I want to say here. There's a well-defined mapping on the 1-1 cohomology. So if you have a bimeromorphic mapping, there's a well-defined pullback mapping. Okay, so you can always pull back positive closed currents, and it's well-defined in terms of cohomology. Now, that's nice, but what's not immediately clear is whether this relates to the subject of dynamics, and what they proved. So this is the Diller-Favre page. Everything is Diller-Favre here. There exists some bimeromorphic map. Okay, you can make a bimeromorphic conjugacy here. So this is our original mapping F, and we have some mapping F hat up above. And if you make a suitable bimeromorphic conjugacy, then in fact F hat star iterated is the same as F hat iterated star. Okay? So I shall say there exists a modification such that this holds. Okay. So what this tells you then is the passage to cohomology in fact is natural when you do this. In other words, there can be some small defect in the way you've represented your mapping, and you fix it up. And with the fixed mapping, the passage to cohomology is functorial. Okay, and I want to call this thing here condition star. Okay. Another theorem is that if you take the spectral radius of F star on H11, okay, this is F hat star on H11, this is a birational invariant or bimeromorphic invariant. Okay, so in other words, it's independent. Whichever way you choose to fix your mapping, the spectral radius is always the same. And what that tells you then is that this answers this first question about degree growth. Okay, so I'm not explaining exactly how you do this, but what you can start with this mapping, okay, and you can do this and then immediately find the spectral radius, and they did this, and so this solves or answers question 1. Okay. Okay. In other words, when you do this, then, well, this answers question 1 in a very general way, in the sense that the spectral radius, I should say, is a number always greater than or equal to 1. And if the spectral radius is greater than 1, then you have exponential growth. If the spectral radius is not greater than 1, they've classified what happens. Now, let me say that this condition, let me see what I want to say here. The second, or maybe the last, this is still on the continuation of the Diller-Favre page. So if rho is bigger than 1, okay, so this gives you sort of the initial classification that tells you whether your birational mapping is sort of dynamically interesting or not. Rho bigger than 1 is the dynamically interesting case. If rho is bigger than 1, then two things. There exists essentially unique up to scalar multiple. This is a positive closed 1-1 current such that F star of mu plus is rho times mu plus. Okay. So there is a positive closed current that's invariant. Okay. And the second thing is that for any Kähler form, say omega, if you take F to the nth, if you pull back omega n times and you normalize it suitably, this thing converges to some constant times mu plus. Okay? So what this tells you is that looking at the behavior on positive closed 1-1 current, so you're looking at the action of how the dynamics works on one-dimensional objects, that says that this thing's an attractor. Okay? Okay? Everything, take any smooth positive closed current. It's not, it doesn't have to be, it doesn't have to be Kähler or anything smooth. It doesn't even quite have, it's more general than just smooth. But anyway, just basically every positive closed 1-1 current converges to mu plus. Okay? So it sort of gives you the picture of, it gives you a rather general picture of what happens in terms of the dynamics on one-dimensional objects. Okay? It tells you that positive closed currents are sort of the right thing to look at. So this, in some sense, sort of answers, or, goes in, well, I'll say answers question 3. Or sort of, this is maybe not a complete answer, but it certainly is a step.
Does it have a geometric interpretation?
Yeah, what is the mu plus? The mu plus, well, what is pullback? Well, pullback is if you had a complex manifold, pullback would be taking a pre-image. Okay? So the thing that you naturally take pre-images of would be stable manifolds. So what this is, the mu plus naturally has, if I were to take a piece of a stable manifold, say through a saddle point or something, and if I were to pull it back, I would just be taking more of it and more of it. Okay, so what this says is that I take a piece of I'll call it a stable disk. If I take a pre-image of a stable disk, look at its current of integration, normalize, then this converges to that. Okay, so this is going to go to some constant times mu plus. So this tells you then that mu plus represents the generalized stable manifold. And it tells you that all generalized stable manifolds are the same. So it sort of settles that aspect. There's only, in some sense, so this, in other words, this is the global stable manifold is nicely written as a current, positive closed 1-1 current. And there's only one. Okay. Now, so, new page. So you have a bimeromorphic mapping. So you also have, well, it turns out, so on your surface you have the intersection form on cohomology, and the pullback under the inverse is the adjoint of the pullback, as it turns out. And so if you do this, so Diller-Favre also showed that in this case you can also do the same thing with the inverse. If F star has spectral radius rho then the inverse also has the same spectral radius, and the inverse is the adjoint of the this is the adjoint of that. Or maybe this is by notation this is the adjoint, but this one is the adjoint of that. That's so. There's also a current mu minus, okay, that F inverse pulls back mu minus and multiplies it by rho. So if we take F star of mu minus, let me see. Well, let me do it this way. F upper star of mu minus would be rho inverse mu minus. So we have actually a pair of currents. Okay, we have a stable current and an unstable current. Okay. Now, the obvious thing you want to do is take the wedge product of mu plus and mu minus and get an invariant measure. I mean, that's obviously natural to do if you can. And if you could do that, that would let you go pass from one-dimensional objects to actually point-wise dynamics, because, you know, one-dimensional currents carry different information from measures. Measures are a point-wise, set-wise thing, and currents carry, you know, tangential information. So here's a theorem with Diller, and that is we have a condition, and this is the condition. Suppose, again, we're supposing that the rho is bigger than 1, and we're supposing that if we take the log of the distance, now what we do here is we look at the indeterminacy locus of F, and we go backwards, and we see how close that comes to the indeterminacy locus of the inverse. Okay? And we take the logarithm of that and divide by rho to the n. And if that's finite, okay, that's our hypothesis. Okay? So if this, so this is some condition, then the mu, you can define the wedge product of these two things. This thing is well defined. Okay. It puts no mu, puts no mass on a pluripolar set or any pluripolar set. Okay. So what that means is when we're looking at our mapping, you know, the place where it is, you know, the singular set, the critical set, that's a set of zero measure. Okay, so in fact, the measure does not see anything but a biholomorphic map. The measure doesn't put any mass on a variety, and so in fact, mu is invariant. Or I should say and. And you can see that, you know, if your wedge product has any continuity property at all, you have to have invariance because you pull back the wedge product and these two rows have to cancel each other. So it's not a surprise. Okay. Also, let me see. I'm going to run out of space here. Mu is mixing. Okay. The next thing is that the integral of log of df, that thing with respect to mu, is finite. Okay? So what this tells you is that you've got an invariant measure, and if this is finite, this tells you then when you go to define the Lyapunov exponents, they're finite. Okay? When you have a meromorphic mapping, there are places where the derivative is infinite, so you're not you don't know. There are points that have infinite Lyapunov exponent, but this tells you that the Lyapunov exponent is finite almost everywhere. Okay? And, well, anyway, so in fact, you can put a second derivative there. And the other thing is, right, the Lyapunov exponents. It's the Lyapunov exponents are, one of them is less than 0 and the other one is bigger than 0. And so it's a hyperbolic measure. Okay. So this is sort of the general framework if you have this condition. Okay. And this condition doesn't always hold. It can fail to hold, but it's not. You have to sort of construct things a little bit delicately to make this fail. I should say that Favre found an example of a mapping that has sort of a rotation, an invariant disk like a Ziegel disk, but it has to rotate. This means that it sort of has to rotate like a Kramer disk or whatever. So it has to. It's rotationally invariant, but it rotates in a way that is very that comes very close to being rational. So sort of.
So mu is a measure.
Mu is a measure. Yes, is a measure.
Finite volume.
You're right. Right. Probability measure. Yes. Mm-hmm. Exactly. Okay. So that is mu. Now, this is sort of the general framework, and I want to. Okay, if I have any time left, I want to illustrate how some of this works for this particular family of mappings, which I think is I hope this family of mappings turns out, as you get to know it better, I hope it entertains you, hope it makes you smile. Now, what do I have in mind here? Okay, so this is the cohomological approach, and so I'm just going to erase this here, and I'm just going to write down what happens with the cohomological approach in the case of R mapping. Okay. So in R mapping, we have a 2 torus. Okay. I can think about it as real or complex, and the picture stays the same. It's convenient. I can have the class generated by a horizontal line. This is generated by y equals a constant. Okay, that's a horizontal line. I can also have a class, say orange, generated by a vertical. That's a class of a vertical, which would be x equals a constant. Okay, and I can see what my mapping is doing on cohomology. Well, if I pull back one of these things, okay, what I'm going to pull back first. Okay, that's the same thing as the preimage of H. Now, H was what? That's y as a constant. Well, y just very conveniently happens to basically be x, and so that becomes x equals a constant. And so this is a vertical. Okay? And if I pull back a vertical, okay, that's x equals constant, so that's the first one here. Okay, so I've got y times a linear fractional transformation, so this is of degree 1 in, so I'm getting a hyperbola. So, okay, so that'll be a vertical, in terms of cohomology, a vertical plus a horizontal. Okay, so that tells me then that our matrix is going to look like, if I've got it right, okay, that way. Okay. Now, what else can I say? Well, the spectral radius of this thing, well, this is just the golden mean, so it would be 1 plus the square root of 5 over 2, okay, bigger than 1. Furthermore, if I take this matrix and I take the powers of it, okay, I get Fibonacci numbers. Okay, get Fibonacci. Various Fibonacci numbers, so it's nice. Okay, nice, well-known bunch of numbers. Now, what kind of complex techniques do you use here? Well, we can use some, it's late in the day, we've already had the professionals doing intersection theory. I'm just going to do elementary school level intersection theory. I'm just going to take intersections of things here in the torus P1 cross P1. So, Okay, so our intersection form, in other words, H intersect H is 0, V intersect V is 0, H intersect V is 1. I mean, that's you know, late in the day, you know. So the intersection form looks like this, okay? And so the adjoint of F with respect to the intersection form is this. Okay, in other words, if this is your inner product, then the adjoint of this becomes that, okay? And so, in fact, then what happens if you take F, I'm doing right here, and I pull this guy back and push this guy forward, okay, I get some calculation with Fibonacci numbers and matrices, and I get some number. Okay, I get some number. Anyway, the point is that what I know from, so I'm saying this here because I'm looking at a real mapping, but what I can say also is if I, so right now I'm complexifying, thinking about this as being complexified, and if I complexify the picture, I know exactly how many intersections I'm going to get in the complex picture. So this is actually a tool that lets you know quite a lot. In other words, in our analysis of this mapping, all we do is do the kind of intersection theory you get in complex space, and then we do some different kind of argument to construct some real picture, and then we can get a lot of real intersections, so you know that you have something. The complex picture gives you an upper bound on what you can possibly have. So if the real number and the complex number are the same, you've just proved a theorem. Anyway, so that is this. Now, so it would be interesting to know what would happen if you looked at this mapping we have and tried to figure out what the current looks like. So could you make a picture of the current? Okay, how would you make a picture of the current? Well, this is making the stable current, okay? In other words, what you do is you just take, actually to make this current, all you would do is take any complex disk and take its pre-images, just keep taking its pre-images, and that would converge to the stable current. And so I have a picture. And so here's what the picture looks like. Let me see, let's try it like this here. Okay. So this is what happens if you take a vertical line and you start taking its height, like this is taking a vertical line and you take its 10th pre-image. Okay. And so what this is you can think of this as representing a cohomological. I mean, this is basically almost the limit. And so this gives you a picture of what the stable lamination looks like. And this also represents the complexification of this. Let me see, I forgot to tell you what parameter I'm using. Okay. I'm using the parameter -2. They can. I'm just going to say the word -2 here. So you can focus here on A equals -2, which is what the pictures are made from. A equals -2, and the thing that's important here is that -2 here is actually what's important is everything involves A being less than 0. And there are two cases, actually. I should say that with this family of mappings, there are actually two cases with A less than 0. One is A less than -1. The other one is between -1 and 0. And somehow the singular case happens to be A equal to -1, okay, because that's non-singular. Okay, when A is -1, your mapping temporarily happens to be affine, and so that's, you know, a bifurcation then in your family. But anyway, as I said, the mapping is reversible. So if I can do the right flip, let me see. I forget which is the right flip. Oh yeah, here's the right flip. Okay, so that'll be the unstable manifold. Okay, And so, in fact, if you put them together, so you'd like to know what is the intersection, so this wedge product of mu plus and mu minus, that's an intersection product. So the intersection product is gotten just by looking at this picture. So one of these pictures is the stable lamination, the other one is the unstable lamination, and you can see that you've got, you can see where the measure is. Okay, the measure has to be at these intersection points. Okay, that's over here and over there. Those two places are where the measure is going to live, and you can just see from the picture what you have, or what you hope to have. Now, so looking at this picture, you can see that you've got a nice, really good-looking, stable lamination. You've got a really good-looking, unstable lamination, and they're intersecting transversally. And for, for anybody's money, this is local product structure over here. I mean, it's not only local product structure, it's you've got two product boxes, so the whole dynamics takes place in two product boxes. So, I mean, that's really like almost global product structure. So, I mean, the thing you want to prove is that this family, for these parameters less than 0, this family of birational mappings looks like an axiom A mapping. That's the plan in the next 22 or something minutes. Okay, so that's the idea is to show that this is, as much as possible, looks just like a birational mapping. Of course, that's a plan, and sometimes the plan is not always going to exactly work. Because, in fact, as you know, the mapping does have places where it's not, not well defined, and it also has places where it's not one-to-one, so it's not actually smooth and it's not actually invertible. And actually also, the other thing is it's got the dynamics actually sort of governed by this parabolic point. So there's also a parabolic point, so it's not actually axiom A. But anyway, we will this picture then, but the picture does really tell you that you can think of this, you can want to think of this as being an axiom A map, and just, it's the end of the day, things need to work right. Okay, so let me say a couple of things. So there's a parabolic point here. The point infinity is a parabolic point. Okay, and that's the only parabolic point, but there is this one parabolic point. And let me say, I guess red is the color of, that's not, it's actually wrong. Green. Okay, so this is, okay, those 4 points are the same point. Okay, so this one is parabolic. And the mapping there looks like a flip. Okay, so we have sort of there's an invariant line, okay, going through this, and there's a flip. So the mapping sort of is flipping back and forth and looks like a translation. It looks like you're flipping, and otherwise it looks like a translation going down here and a translation like that. Okay, that's what this mapping looks like. So down there near infinity, you have that happening. And so the flip means that this portion flips over to that portion. Okay, they two flip back and forth. Okay. So, oh yeah. So anyway, we've got the parabolic fixed point. I'll say something about the parabolic fixed point in a second, but let me say the second place where intersection theory gets used is this. So we now know exactly what the mapping is doing on cohomology, so you can use the Lefschetz fixed point theorem. Okay, and so what does that tell you? That tells you that if you look at the trace of f star to the n on the total cohomology, that gives you the number of points. Okay, let me write this. Okay, so this is with multiplicity. This will be the total trace on cohomology. Okay, now what's the deal here? We've got our space is P1 cross P1. Okay, So there is cohomology in dimension 0, dimension 1, 1, and dimension 2, 2. Okay, so so we have H0, H11, and H22. Okay, so these two are one-dimensional, and so the trace is just going to, it acts as the identity on those, and so the trace of each one of those is 1. So it's an alternating sum, of course, but there's nothing in this dimension and nothing in that dimension, so the negative things aren't there. Okay, so we have that plus then the trace on this one. Well, we know that this is exactly what the mapping looks like, so we have Fn minus 1 plus Fn plus 1. Okay, so we know exactly with multiplicity what the sum of all the periodic points, what the number of periodic points is going to be. And let me say that you can check that the multiplicity of the, I want to say that f to the n at the point p infinity. Okay, so this is going to be 2 if n is odd, and 4 if n is even, and not 0. Okay. So there's one. It turns out that this parabolic point is the only non-finite point that's fixed or periodic, because in fact the mapping at the lines at infinity acts like a translation. It's flipping and just acts like a translation. So there are no periodic points out at infinity, except the point infinity, infinity. Okay, so again, this is another nice tool because this tells you that when you're looking at the real mapping, if for some real reasons you can come up with a lot of fixed points, then you know exactly when you found them all because you know how many complex. So I should say this is the number of complex fixed points counted exactly. Okay. So there's sort of you can look at the stable set of this point at infinity. And let me just remind you, this is going to be all the points x such that f to the n of x is never in the indeterminacy set. Okay, I mean, you have to rule out the indeterminacy set, and f to the n of x goes to p infinity. Okay. That's this thing. And there's also the forward basin. Okay, this is the forward basin of the point at infinity, and this is the set of all the points x such that there exists a neighborhood u such that f to the n of u goes to p infinity uniformly. Anyway, you can prove that b plus is the interior of this thing. And another theorem is that if we look at the closure, this is the non-wandering set. Okay. And just by the by, b plus intersect, so b minus is the backward basin of infinity. Okay. This is dense. And we don't know how to prove it, but I figure it must be full measure. Who knows? But anyway, when these people were looking with the computer and everything, they never found any non-trivial dynamics. So this is one explanation. Why not? Is that, everything basically is in the basin of infinity. So you either go to infinity uniform, a neighborhood goes to infinity uniformly in forward or backward time for a large set. Okay, now what we'd like to do is capture the dynamics by introducing a Markov partition and showing that the symbolic dynamics works out correctly on a Markov partition. So, what we do to take our Markov partition, let me consider both of these pictures in the same place. Okay? So what I want to do is consider the line x equals 1 and the line y equals minus 1. I want to consider these two lines. I want to take this piece down there, and that'll be one of my pieces of the Markov partition. And the point here is that I'm taking a to be, well, okay, here I'm taking a to be less than minus 1. If a is less than 0, I take a slightly different picture. But anyway, less than minus 1, then this line will be on top, and the other critical line is down below. That's sort of what happens. Now, well, I'll just cut to the chase here instead of explaining why. This is R1, okay? So that's R1 and this is R0, and what we do is a little lemma says that if I take f of R1, it never intersects. In other words, we know that out here near infinity, this one flips to the other side. So out near infinity, this flips out there, and in fact, R1 gets mapped forward across something like this. And R1 is disjoint from its image, okay? And so that tells us then, what we want to do is consider, the standard thing of we want to consider orbits that lie in R0 and R1 in all time. That means you can code them by their itineraries, okay? So what we do is we consider this thing here to be the golden mean shift. That'll be all the sequences. These are sequences of zeros and ones such that there's no 1, 1. In other words, every time you've got a 1, it has to be followed by a 0 or preceded by a 0, both. Okay, so this is that subshift. And we define the rectangle for any S in sigma G, we define the rectangle to be the intersection of, and then we remove the point at infinity, that one point at infinity. Okay? And it turns out that this point at infinity is that parabolic point, and that's a problematic point. The point at infinity somehow corresponds to the 2 cycle of 0 and followed by 1. Okay? In other words, here we have there's a unique fixed point which is 0 forever. Okay? You can't have 1 forever because that's forbidden. But then you have a 2 cycle, 0, 1, and 1, 0. Okay? And both of these we define to be the point at infinity, that particular parabolic point. Okay? And for the rest of them, this is, by definition, this is all the points that have itinerary S. Okay? Now, what I should do here, I think, is just state a theorem. Okay? Okay. Let me do one thing first here. I've been talking about the complex picture. There's also the real picture here. This is any curve in R0 that connects the top to the bottom will be called an S arc. Okay? And any arc in R1 that connects the sides will also be called an S arc. Okay? And U arcs are ones that go, so this stands for stable, obviously. U arcs are the ones that go the other direction. Okay? So obviously, if you're in R0, every S arc intersects every U arc. And in R1, every U arc in R1 intersects every S arc in R1. Okay? And so we have a little lemma here, little combinatorial lemma. Okay, and that is that if you take the pre-image of an S arc in R1, this contains an S arc in R0. Okay, so if you take this S arc and map it backwards, it's going to go to something or other that it's going to go through R0 and at least an S arc and maybe more stuff. And so F inverse of an S arc in R0 is going to contain an S arc in R0 union with an S arc in R1. Okay? So this is the real analog of what was happening with the mapping on cohomology. Before with cohomology, if you had a vertical and you pull it back, you get a vertical plus a horizontal. And if you have a horizontal, you pull it back and you get a vertical. Okay, so this is the real analog. Okay, and so so what I want to say is that if you instead of an S arc, if you actually make it a straight line, okay, then pulling back a real arc and pulling back a complex line are the same thing. And with the complex intersection theory, you know how many intersections a complex thing will have. Here you know that there have to be a certain number of real intersections when we intersect stable things and unstable things. And so here we know that we have at least enough. By complex intersection theory, you know that you have a precise count with multiplicity. And so that tells you when you're taking stable arcs and unstable arcs and pulling them back and pushing them forward, you get exactly the right number, not too many, not too few, and they're also transverse. Okay, so I'm just advertising that as a method that you can use to actually prove things. Anyway, so I promised you I'd stated a theorem. I would state a theorem, and let me just state a theorem, and then I'll be finished. So, here's a theorem. Okay. So in fact, what we want to do, this is your code, this is your proposed coding by an itinerary. You'd like to say that there's exactly one point with that code, okay? And that's almost right, okay? However, let's define W star to be the sequence that has 0 in the 0th space, and then carries on as in like this. Okay, so that's W star. Okay, it turns out that the rectangle corresponding to W star is an interval at infinity. So it's an interval, but unfortunately it's a non-trivial interval. Okay, and on the other hand, if S is not in the orbit of W star, that's equivalent to R of S being a point. Okay? And I think I just have enough room to state a theorem then. What this tells us then, we can look at the golden mean shift and this procedure of constructing the rectangle takes any sequence and basically gives you a point, and this space here we're going to call defined to be. This will be the union of all the rectangles. Okay. And so this is basically, except when we're on the orbit of this thing, the W star, this is a mapping taking points to points. And we also have that R composed with sigma, in other words, the shift map on S would be F of R of S if a point of indeterminacy is not in other words, if the particular point of indeterminacy, that's the point minus A infinity, okay, if that point is not in this rectangle, so in other words, these things are all points except for this one case, and if this one is not in there, then we have this. So what this tells us then is that this model here of the golden mean shift is mapped forward by this mapping R to to omega, which is the union of the rectangles, and that is as much of a semi-conjugacy as you can have, because, of course, this thing is a homeomorphism, and this thing's not a homeomorphism. And I should say that this is the non-wandering set. So another theorem says that this thing is the non-wandering set. And if we take the measure mu that was given by the general theory here, just underneath here, this is the wedge product of mu plus and mu minus, R pushes forward the maximal entropy measure of this thing to the measure you get over here. So this tells you what the entropy of this map is, and this tells you also that this tells you that the complex measure coincides with the measure from symbolic dynamics, and this tells you then that the dynamics of this thing is basically given by this golden mean shift. So that's it. Thank you.
The first term is stated there was a summability condition.
Yes.
How does it relate to parameters? How does it?
For these things?
Yeah.
Oh, it can't happen. The thing is, with in this case, the only thing that can see what happens here is when you're looking at the points of indeterminacy, saying going backwards, and this point of indeterminacy going backwards, they're both going back to the same point. It's very difficult for that condition to fail. Okay, you're taking the distance of how quickly you're converging, you're taking the log, and then you're dividing by some power of rho. The only way you can make it not hold is to have some kind of Kramer disk. So you have to have a invariant thing rotating around. You have a point of indeterminacy and the other point that's coming around, and now and then it has to make very, very close returns. And that's the only way you can do it. Oh, thank you. Oh, thank you. I really think these mappings are very interesting.
Yeah, sure.
A lot of fun.
And in the real, you can see everything. Huh?
Yes, yeah, that's nice. It's pleasant. Otherwise, you've...
Sure. Very well.
How much does it depends on the parameter?
Oh, A has to...
The condition.
Oh, this condition that I raised, it's very difficult to create that. So, like with this family, it cannot happen.
Oh, in this family,
No.
for all A, independent of A.
Yeah, it cannot happen.
Oh.
It's difficult to construct an example. I mean, sorry, I said it wrong. Of course, what the thing is, it's difficult to construct a family for which this can happen.
You can have more specific examples, but here, independent of A, you have all is very supported in this. The support is like the Kendall set.
The support is all inside I. Make it clear. When A is negative, the measure is real. When A is positive, the measure is probably all around.